Let a set B together with operations addition, multiplication and complementation defined on it, and also if it contains two identity element 0 and 1. 0 is the identity element with respect to addition and 1 is the identity element with respect to multiplication. Suppose this structure is a Boolean algebra. Then a non-empty subset S of B is said to be subalgebra or Boolean subalgebra if S itself is a Boolean algebra with respect to operations addition, multiplication and complementation of B. It means S is said to be a subalgebra if it is closed with respect to operations of addition, multiplication and complementation which are defined as on the set B. So it is clear by the definition that for any Boolean algebra B, the subset 0, 1, where 0 is the identity element with respect to addition and 1 is the identity element with respect to multiplication, then this set 0 and 1 is the uh, Boolean subalgebra of B. Also, B itself is a Boolean subalgebra of B. It means the set 0, 1 and B are both subalgebras of B. Also, the identities of addition and multiplication which are 0 and 1 must belong to every subalgebra. Because if S is a subalgebra of Boolean algebra B and A belongs to S, then by complement law, A dash also belongs to S because it is closed with respect to complementation. So it means A plus A dash is equal to 1 because S is closed with respect to addition. A into A dash is equal to 0 because A is closed with respect to multiplication, therefore A plus A dash and A into A dash must belongs to S. It means 1 belongs to S and 0 belongs to S. It means every Boolean algebra must contains the identities with respect to addition and multiplication which are nothing but 0 and 1. Now we have one result. A non-empty subset S of a Boolean algebra B is a subalgebra of B if and only if S is closed under the three operations of B. What are the three operations of B? Addition, multiplication and complementation. Suppose S is a subalgebra of a Boolean algebra B. Then by definition S itself is a Boolean algebra under the three operations addition, multiplication and complementation which are defined as on B. It means S is closed under the three operations. Suppose A and B belongs to S, then it means A plus B belongs to S, A into B belongs to S and A dash belongs to S. It means S is closed with respect to addition. It means S is closed with respect to multiplication. It means S is closed with respect to complementation. So this is the first part of the theorem. Now for the second part, suppose that S is closed under the three operations addition, multiplication and complementation of B. Means if AB belongs to S, then A plus B belongs to S, A into B belongs to S and A dash belongs to S. Now we will show that S is a subalgebra of B. Since S is a non-empty set, therefore suppose A belongs to S. It is given that S is closed with respect to complementation. It means A dash belongs to S. Now A belongs to S and A dash also belongs to S. And S is closed under addition. It means A plus A dash belongs to S. Also A belongs to S, A dash belongs to S and S is closed with respect to multiplication. Therefore A into A dash belongs to S. But A plus A dash is nothing but 1. And A into A dash is nothing but 0. It means 1 belongs to S and 0 belongs to S. Means both identities 0 and 1 are in S. Now we will show that all the four axioms are also satisfied for S. Suppose A and B are any two elements of S. Therefore, A plus B is equal to B plus A, and A into B is equal to B plus A, because if AB belongs to S, then AB also belongs to B, and B is a Boolean algebra. Therefore, commutative law with respect to commutativity with respect to addition holds in B, and commutativity with respect to multiplication holds in B. Hence, commutative laws hold in S also. Now, for any A belonging to S, we have 0 and 1 belonging to S, such that A plus 0 is equal to A and A into 1 equal to A for all A belonging to S, because A also belongs to B and B is a Boolean algebra. Therefore, these conditions are satisfied for S also. Hence, identity laws hold in S. Since operation of addition and multiplication are distributive over each other for all the elements of B, therefore they must also distribute over each other element for each other for all elements of S, because S is a subset of B and elements of S are the elements of B also. Hence, distributive laws hold in S also. Now let A belongs to S. Then by assumption, A dash belongs to S, because S is closed with respect to complementation. And A plus A dash is 1 and A into A dash is 0. Hence, complementation law hold in S also. And all the four axioms are satisfied, as S itself is a Boolean algebra under the operations of B. Thus, S is a sub algebra, or we also call it Boolean sub algebra. Now, one example. Let B be any Boolean algebra and A belongs to B, such that A is not equal to 1. Then the subset, which consists of A dash, 0 and 1, is a sub algebra of B. In the last result, we have shown that a non-empty subset S of a Boolean algebra B is a sub algebra if and only if S is closed under the three operations. So, to prove that this is a sub algebra, it is sufficient to prove that S is closed with respect to three operations. For this, we will construct a composition table and show that the S is closed with respect to addition, S is closed with respect to multiplication, and S is closed with respect to complementation. And for this, we will use A plus A plus A equal to A into A equal to A, and A plus 1 equal to 1, A into 0 equal to 0 for all A belonging to B. So it is easy to construct composition tables because with respect to B, with respect to addition, we know that A plus A equal to A plus A dash equal to 1, A plus 0 equal to A plus 1 is equal to 1. I have written all the elements of S this side and this side. On the top, in the top border row or in the extreme left column. Now, and plus I have written here. So A dash plus A is 1, A dash plus A dash is A dash plus 0 is A dash, and A dash plus 1 is 1. 0 plus A is A, 0 plus A dash is A dash, 0 plus 0 is 0, 0 plus 1 is 1. 1 plus A is 1, 1 plus A dash is 1, 1 plus 0 is 1, 1 plus 1 is 1. I have made use of these identities. Now the composition table for multiplication. So these are the elements of S in the top border row and in extreme left column. A dash 0 and 1, and this is multiplication. A into A is A into A dash is 0, A into 0 is 0, A into 1 is A. A dash into A is 0, A dash into A dash is A dash into 0 is 0, A dash into 1 is A dash, 0 into A is 0, 0 into A dash is 0, 0 into 0 is 0, 0 into 1 is 0, 1 into A is A, 1 into A dash is A dash, 1 into 0 is 0, 1 into 1 is 1. And this is complementation. Complement of A is A dash, complement of A dash is A, complement of 0 is 1, and complement of 1 is 0. And it is clear from all the three tables that all the entries in the tables are elements of S. Therefore, S is closed with respect to addition, multiplication, and complementation. Hence, S is a subalgebra of B, or S is a Boolean subalgebra of B. Now one more result. If S1 and S2 are two subalgebras of Boolean algebra B, then S1 intersection S2 is also a subalgebra of B. Suppose S1 and S2 be any two subalgebras of Boolean algebra B. We know that Boolean sub algebra always contains identity elements. Identity element with respect to addition, which is 0, identity element with respect to multiplication, which is 1. So 0 and 1 always belong to Boolean subalgebra. Therefore, S1 intersection S2 is non-empty because 0 and 1 belongs to S1 intersection S2, because 0 and 1 belongs to S1, S1 is the subalgebra, 0 and 1 belongs to S2 and S2 is a subalgebra. It means 0 and 1 belongs to S1 intersection S2. It means S1 intersection S2 is non-empty. Now suppose A and B belongs to S1 intersection S2. It means AB belongs to S1 and AB belongs to S2. But S1 is a subalgebra. It means S1 is closed with respect to operations of addition, multiplication, and complementation. It means A plus B belongs to S1, A into B belongs to S1, and A dash belongs to S1. Also, S2 is a subalgebra. It means A plus B belongs to S2, A into B belongs to S2, and A dash belongs to S2. Because A plus B belongs to S1 and A plus B belongs to S2, it means A plus B belongs to S1 intersection S2. Similarly, AB belongs to S1, AB belongs to S2, it means AB belongs to S1 intersection S2. A dash belongs to S1, A dash belongs to S2, it means A dash belongs to S1 intersection S2. Thus, S1 intersection S2 is a subalgebra of B. Thank you.